To remind you, we're in the section 3.4, rates of change, and we covered an example coming from geometry. Next, we'll go over an example coming from economics, and finally, one from physics. So, for the quiz and for the next midterm, you should expect to see one of these applications, not perhaps the same numbers, of course, but typical problems. This is kind of an easy part of the second midterm, so typical problems. From rates of change section, or either metric, which is what we just saw. Now, economics, and finally physics. This is what we're going to see now. I just gave you an introduction. I mean, give more explanations that were actually required for you for the previous example, just to be thorough. But in general, if you're asking to change, say, I mean, variations of what we went over for the last video would include, say, how what is the change of a rectangle if the diagonal or the side increases from, say, 5 to 5.01. And this just means that you need to compute the area as a function of the side, and then take the derivative of that function and evaluate the 0.5, because you're evaluating, I mean, you're considering a small perturbation of the side of 0.01. So that's basically it. So those kinds of questions are almost always the same, and so there's not much mystery there. And when you're asked to find, well, why is the derivative bigger at a certain point than another, you can give your explanation along the same lines as we did before. I mean, if we look at, I mean, the area is proportional to the perimeter, to half the perimeter, or something like that, and then therefore, as you increase, say, the side of a rectangle or a square, then naturally the smaller changes are gonna lead to the bigger changes in area, the larger the perimeter, the initial perimeter was. So things like that. Now for the next example, this is an example actually that does not make a lot of sense from the point of view of mathematics, but it is very used in economics. Partly because, I mean, things are happen. I mean variations tend to be very small on large scales for the functions involved in economics, that even though you may move a lot along the x-axis, the changes you expect to have in the value of the function are really small. So the graphs look kind of flat. So because of that, f prime is a good approximation of the change in unit for one additional unit. So I mean, these are all words, but let's be more specific. So for small values of h, the difference difference quotient is close to the derivative itself. So this brings us back to the previous video. The f prime of x naught is well approximated by this quotient. This is the second form of the derivative, if you remember, if we take h going to 0. So for small values of h, this should be a good approximation. So this approximation here improves as h gets smaller. So typically we think of h as being 0.00001, point 0.0000001 or something much smaller than that. But in economics, it seems that h equals 1 is small enough to make this a good approximation. And if we set h equal 1, set h equals 1 in the formula up here in this approximation, what we obtain is the following. So we get that f prime of x naught is f of x naught plus 1, approximately f of x naught plus 1, minus f of x naught divided by what? By 1. So we get this expression. We get the simple, very simple expression just by setting h equals 1. In general, as I said, setting h equals to 1 is not a good approximation of them, doesn't give you a good approximation of the derivative. For functions that don't change that much, it can be, I mean, in the thing is in the context of economics that's the case, but in general this would not be a very good approximation of the derivative. But the interpretation here is what's most important when you want to tackle these kinds of problems. F prime of x naught is approximately equal to the change in f cost by a 1 unit change in x, where so at what point when x is equal to x naught. This is what's called the marginal cost. So it's the in economic context, so if you are at a certain production level, the cost of producing one more unit, one additional unit at production level, say x naught, is called the marginal cost. and so this is what we discuss next. So usually what we have a cost function c of x cost is of course given in dollars of producing x units of a product. Now we have the production also. And this is the number x of units. This is production level is what we said, the number of x of units manufactured. That's what I said, that the marginal costs is the cost of producing one additional unit at a given production level. So now the very important concept of marginal cost, and this is of course at production level x naught is cost of producing one additional unit at this production level. So the formula is the following: marginal cost is c of x naught plus 1 minus c of x naught. Now the point here is that we can estimate the marginal cost at a given production level x naught by simply taking the derivative of the cost function. And this is the approximation formula that we will be using. Okay, so again, going back to the marginal cost, I said that there was the cost of producing one additional unit at production level x naught. Of course, if you think of, producing one additional donut, say if we have already produced 100, so the cost of the additional one is the cost of producing 101 minus the cost of producing 100. So this need not be constant. And the idea here is that usually the marginal costs are decreasing. At least in certain ranges, because for instance, if you need storage, you just need to, whether you have 20 or 30, you plan to produce, 20 or 30 units of a good, I mean, you have to pay the same, you have to pay the rent, and you have to pay the same no matter whether you produce 20 or 30 units. So for each additional unit, your costs don't increase due to paying rent. Okay, so that decreases the marginal cost, for instance. But okay, this is not an economics class. It's just so that you have an idea of what we are doing here. But then the next video will be just going over a couple of examples, and hopefully from there uh, you'll get what the section is about. I mean, there's not much more than notation. Uh, Remember, this is calculus, so basically everything we'll be doing will be asking you to find derivatives and do something with those derivatives. Here, the part we need to differentiate here is to approximate this increase in one unit in the cost function. Okay, so let's let's move on to the next to the examples. We'll cover those in the next video.